All right. Thank you for coming to this session. This session is titled Modeling Gravitational Waves. So we're going to have 3 speakers, then a 10-minute break, then 2 speakers. Okay, let's get started. Our first speaker is Wai Chung from the University of Illinois Urbana-Champaign. Do you want to share your screen?
Okay.
All right, so I will give you a warning when you have 3 minutes left. Please go ahead. So our speaker is Adrian Chung, and he will be talking about spectral method for computing gravitational quasi-normal mode frequencies of black holes. Great.
Hello, everyone. I'm Adrian, a postdoc at Professor Yunes' group at UIUC. I'm also a member of ICASU, the Illinois Center of Advanced Studies of the Universe. Today, I'm going to talk about spectral method for computing gravitational quasi-normal mode frequencies of black hole. But before I talk about the method, I will briefly remind you what black hole quasi-normal modes are. So black hole quasi-normal modes are the characteristic oscillatory modes of a per-adapted black hole. A per-adapted black hole can be produced in compact binary collision. After the merger phase, the distorted Raman black hole will settle down into a stationary black hole through undergoing a series of damped oscillations and generating gravitational waves that are equally exponentially decaying in time. The frequencies of the oscillations and gravitational waves are known as the quasi-normal mode frequencies. But why should we care about black hole ring down phase or quasi-normal modes? Because they are potent probe of fundamental physics in the strong field regime, such as the space-time near the event horizon. If general relativity breaks down near the event horizon, the space-time near the event horizon will be different from those described by general relativity. That will entail different quasi-normal mode spectra. So we will measure quasi-normal mode frequencies that are different from those predicted by general relativity. Such discrepancy could be the smoking gun evidence that general relativity breaks down near the event horizon. Alternatively, if matter or energy presents near the event horizon, the gravity source by the matter and energy will affect the gravitational waves propagating around the around the per-adapted black hole. That will also equally change the quasi-normal mode frequencies, making them different from those computed by assuming the Raman black hole to be vacuum. So these 2 connections suggest that we can probe numerous unknown physics by measuring quasi-normal mode frequencies. But to carry out this test, we need to compute the gravitational quasi-normal mode frequencies of black hole under different circumstances. Unfortunately, the existing method only allows us to compute the quasi-normal mode frequencies of limited black hole models. So to fully realize the potential of the ring down test and to tackle this difficulty, my collaborators and I at UIUC are developing a spectral method to compute that allows us to compute the quasi-normal mode frequencies of a black hole under generic circumstances, regardless of the geometric classification of the background space-time, as well as whether the black hole is vacuum or not. Spectral functions are complete and orthogonal, meaning that we can accurately approximate a differentiable function by using a linear combinations of just a handful of spectral functions. For example, if I would like to approximate the differentiable function represented by the blue curve in the figures, I only need 6 spectral functions to accurately approximate it, to an extent that the difference between the approximation and the original function are barely visible in the figure. This is an extremely powerful property for us to compute gravitational quasi-normal mode frequencies, because we can just express the metric perturbations around the per-adapted black hole as a linear combinations of the spectral functions. So the overall idea of the spectral method can really be summarized by this roadmap. We begin by considering a tiny metric perturbations on top of the background metric, as given by G mu nu 0 and H mu nu. Then we estimate the asymptotic behavior of H mu nu, the metric perturbations, at the event horizon and in spatial infinity. Using the asymptotic behavior, we can construct an ansatz for the metric perturbations as a linear combination of spectral functions, with A mu nu being the spectral coefficients of the metric perturbations. We then substitute the ansatz into the linearized Einstein field equations, and we similarly expressed the linearized Einstein tensor as linear combinations of the spectral functions, with B mu nu being the spectral coefficients of the linearized Einstein tensor. As far as vacuum perturbations are concerned, the orthogonality of spectral functions imply that B mu nu has to be 0 for all m and. But B mu nu are not free parameters. They are related to the spectral coefficients of the metric perturbations through linear combinations. So what we have in the end is a system of linear homogeneous algebraic equations of A mu nu. But for detectable ring-down signal, A mu nu cannot be all 0. Then by a very fundamental theorem of linear algebra, that just means that the quasi-normal frequencies have to be some eigenvalues associated with the resulting linear homogeneous algebraic equations of A mu nu. To cut the long story short, that just means that if we get the eigenvalues, we get the quasi-normal frequencies. For the interest of time, numerous technical details cannot be covered here. If you're interested, I strongly encourage you to check out this paper on PRD. So we first validate the method by applying it to compute the quasi-normal frequencies of black holes in general relativity. Here I'm showing you the results of applying the method to compute the frequencies of the Schwarzschild black hole, which is the non-rotating black hole in general relativity. So the horizontal axis is the real part of the frequencies, and the vertical axis marks the imaginary part. The quarks represent the known quasi-normal frequencies of the Schwarzschild black hole computed using the existing method. In general, at a given number of spectral functions, which is the capital N shown in at the top left corner of the figure, there are many eigenvalues. To avoid overcrowding the figure, I'm just showing you the eigenvalues that are closest to the known quasi-normal frequencies. But after all, so the eigenvalues, the closest eigenvalues are represented by blue dot. But after all, we also develop a method to keep track of the eigenvalues that allows us to select the physically meaningful eigenvalues that correspond to quasi-normal frequencies, which are also the eigenvalues closest to the quarks. So I'm going to play you a video. So as you can see that as we gradually increase the number of the spectral functions included in our ansatz, the closest eigenvalues are aligned more and more closely with the known quasi-normal frequencies until in the end, the eigenvalues overlapped with the known quasi-normal frequencies almost completely, almost perfectly in the complex plane. So these results suggest that if sufficiently many spectral functions are included, we can accurately compare the quasi-normal frequencies. So what is more important is to take the rotation of black hole into account. Here I'm showing you the results of applying the spectral method to compute the fundamental co-rotating quadruple mode frequency, also known as the O22 mode frequencies of the curved black hole of dimensionless spin from 0 to up to 0.95. So the solid line traces the trajectory of the O22 mode frequency in the complex plane as a function as the dimensional spin increase from A equals to 0 to close to 1, and the frequencies is computed by the Tchaikovsky equations. The dots represent the frequencies computed using the spectral method. As we can see that the dots are lined on the trajectory completely, almost completely. That just indicates that the spectral methods can accurately compute the O22 mode frequencies of the curved black hole up to dimensional spin of 0.95. This is highly non-trivial. I want to emphasize that each dot are computed by solving the 6 linearized Einstein field equations simultaneously using the spectral method. Each linearized Einstein field equations consists of several thousand to several 10,000 terms. And such a length and complexity implies that decoupling or the definition of master functions are impossible. But despite the length and complexity, spectral method can just be applied well and good to accurately compute the O22 mode frequencies, which is expected to be the dominant mode that will show up in the ring down signal detected by the ground-based detector. So I believe this result showed you the strong potential of the spectral method that we developed to be readily adapted and generalized to compute the O22 mode frequency of other black holes whose linearized field equations are equally lengthy and complicated, because our method does not require any decoupling or fancy advanced mathematical and algebraic manipulation. We then perform a polynomial fit to these O22 mode frequencies computed using the spectral method, and we use the polynomial fit to analyze the actual data of the first detected gravitational wave events, which consists of the ring down signal of the event. So in the left panel, I'm showing you the two-dimensional posterior of the Raman mass and Raman dimensional spin that obtained using the O22 mode frequencies computed by the spectral method and those computed using the Tchaikovsky equation. So the blue contours are the confidence interval of the posterior obtained using the O22 mode frequencies computed using the existing method by solving the Tchaikovsky equation. And the red contours are the confidence interval of the posterior obtained using the polynomial fit to the results of computed using the spectral method. And the quartz represent the median published by the LIGO and Virgo collaborations. As we can see that firstly, the contours of the obtained using the spectral method results overlap very well with those obtained using the frequencies computed by solving the Tchaikovsky equations. This indicates good consistency between the results that obtained using our method and those obtained using the existing method. And secondly, the 95% confidence interval of all the contours enclose the median published by LIGO and Virgo. This indicates good accuracy of the results obtained using the spectral method. So in the right panels, I'm showing you the marginalized posteriors of the Raman dimensional spin and Raman mass obtained using the two different spectra. So the marginalized posterior looks almost identical despite some fluctuations due to the random nature of the stochastic sampler. So this also indicates good consistencies of the results produced by our method and that produced by the existing method. So these results show you the strong potential of a spectral method to be applied to produce results that are applicable to be applied to the analysis of the actual gravitational wave data analysis.
Excuse me, if you could wrap up in the next 2 minutes, that'd be great.
Great, sure. So that's my final slide. So in summary, we developed a spectral method that can accurately calculate black hole quasi-normal frequencies. And most importantly, the method can easily be adapted or generalized to other black holes that is beyond general relativity and that is not vacuum. Holes linearized field equations are extremely lengthy, complicated, and cannot be decoupled. So I believe these results already showed you the convenience and the advantages of the spectral method. So in short, the spectral method makes black hole perturbations easier. And nowadays, as we can detect black hole wing-down phase more and more loudly, more and more clearly, black hole perturbations calculations will be more and more important in the future development of gravitational wave astrophysics. And this method could be more and more helpful for us to analyze the detected ring-down signal, and those will be detected in the future. So again, for the interest of time, many technical details cannot be covered here. I encourage you to check out this paper. So this is the end of my presentations. Thank you.
All right, thank you very much. All right, we have time for questions. You can type your question in the, you can either type your question in the Q&A or you can raise your hand. Yes, Lisa?
Hi, can you hear me?
Yes.
Yes.
Hi, I have maybe a very naive question. So as you've said, the advantage is that it's easy to generalize it to like beyond GR black holes. Is it also faster to compute, or is it like of the same order in terms of the speed?
Well, honestly, I do not quite sure about the answer, because many existing methods cannot compute the quasi-normal mode frequencies of the black holes, which we expect the spectral method can also be applied. So formally, the time needed for those methods to compute the quasi-normal mode frequencies will be infinite, but for us, that should be finite. But of course, it will also take you some computational power to compute the frequencies. But the difference is that for the existing method, the computations will almost be impossible. But for us, at least in principle, we can just apply the method with some easy, straightforward adaptation, and then we can just send it to cluster and then compute the frequencies. So I will stress the difference is rather between impossible and possible rather than in terms of time. So of course you have to devote some times, but the methods can almost guarantee you, not guaranteed, but it's very likely to succeed in computing the frequencies of the black holes, which other methods cannot apply.
Gotcha, thank you.
Thank you.
All right, other questions? All right, if not, thank you. Our next speaker is Michael LaHaye, and he will be telling us about efficient, fully precessing gravitational waveforms for binaries with neutron stars.
Okay, yeah, thanks for having me. So this is something I've worked with Béatrice, Huan, and Zhenwei about. We published a paper that's going up on PhysRev soon. And yeah, I'm a PhD student from the University of Guelph. Okay. So initially the idea here was that you have these mass gap objects like 190814, where, you know, for some reason or another, you want to tell them apart from black holes, maybe to be able to say something about the populations of black holes or neutron stars. If it's a very heavy neutron star, that tells us something about the neutron star population and vice versa. And same with black hole mimickers. You want a way to distinguish them from black holes as well. Now, there are several possible ways that you can look at the nature of an object. One would be the tidal deformability. So as we know in GR, this should be 0. So getting a non-zero amount of this should be telling. You have potentially EM counterparts if we see them. You have horizon absorption. And then you have the effect that we developed a model for here, the spin-induced quadrupole model. So any one of these things could tell you the difference. But because we cared about mass gap objects, typically the tidal deformability that you might expect is like O of somewhere around 10. And currently the best constraints that we can place on this are equal to or less than 800. So at the moment, we can't really tell the difference between a black hole and some other object via the tidal deformability. And this may continue to be true even into the era of third generation detectors. It might just be the case that we simply, even then, aren't sensitive enough to tell the difference. It's unclear at the moment whether we'll be able to. Now, horizon absorption, typically an even smaller effect than this. So if we're not measuring that, we're not measuring the horizon absorption. And yeah, EM counterparts are very informative, but we can always miss them if we don't have good sky localization for any number of reasons. So not seeing it isn't necessarily evidence of anything. So given that any one of these other methods can fail to be informative about the nature of an object, we wanted to kind of complete the picture for this fourth avenue to investigate the nature of objects. Okay. So our waveform model, it's an extension on the RMR phenom XPHM. The changes that we've included, so we've included this correction due to tidal heating, so not new to us, we're just including it. You have the phase modulations due to the spin-induced quadrupole moment. So we've referred to this as the aligned effect because even for spin-aligned systems, it's present. This, again, has been included before. It's been included in the TGR analysis. And then finally, we have the effect that we are adding in. So the effect that kind of completes the picture, the corrections to the precessing sector. Okay. So in principle, tidal corrections are not difficult to include. We didn't include them here because kind of the initial idea was that we wanted to look at mass gap objects for which tidal effects are largely not relevant, but in the future, easy to include. And to give you kind of a comparison to other waveform models, so spin-Taylor numerically evolves the 3PN spin dynamics. We're semi-analytically evolving the 2PN spin dynamics. So obviously you have a loss in accuracy there, but there's a significant timing and speed up. So over one particular range and parameter space, the speed up is as much as 10 times. Okay, so a factor of 1 second versus 100 milliseconds. And we believe that because of the framework that we've come up with, that it's not difficult to add these higher PN corrections at a later time. So I guess to talk about what we did. So previously, the way that this was typically done is you want to evolve this set of 3 angular momenta, so the 2 spins and the orbital angular momentum. And this would require, some set of 9 scalars, some of which are conserved quantities, and the other are dynamic variables. It's been shown that for binary black hole systems, there's this set of 7 conserved quantities. So the 3 magnitudes of the angular momenta and the 3 components of the total angular momentum, and then this chi effective. Okay. And then the choice for the other 2 dynamic variables is kind of arbitrary. We choose this delta chi, which, if chi effective is the sum of the projected reduced spins, then delta chi is the difference. So kind of analogous to each other. And then you have this other dynamic quantity that describes how much the orbital has precessed around the total angular momentum. So one of the Euler angles. So When we move to the neutron star, so from black holes to neutron stars, chi effective is no longer conserved. And the main effect of this is that the system precesses faster. Okay. Usually faster, like it depends on the spin tilts. It can precess slower. It modifies the precession according to like the projection of the spins. So, okay, great. We've included this correction. I guess one thing that we want to determine is, which one's going to tell us the most about the spin-induced quadrupole moment of a body. So here what we've done is we've taken a system, we've generated a binary black hole waveform, and then we've taken that same system and we have the three effects that we're accounting for, and we turn on one of the effects at a time and compare the mismatch between these two waveforms. And we do this for the three different effects. And what is shown here is a CDF of the mismatches for each of these three effects and a fraction of the total mismatch. So in practice, the mismatches don't actually add up like this, but here we're trying to get some measure of which is the most important. So what we find is that, generically the aligned effect is the more important. It makes up 70% of for 70% of the time, it makes up the majority of the mismatch. Okay. But this does mean that, 20 to 30% of the time, the precessing effect is more important. So just 30% of the time, we have to care about this effect. But right now, even though it seems that generically the aligned effect is more important just in terms of the mismatch, that really doesn't tell us how well each effect is going to constrain kappa. And there's kind of a reason for this. The aligned effect turns out to be degenerate with changes to the component masses and spins. So if you have an aligned waveform that includes the spin-induced quadrupole moment, like Taylor F2, the effect is completely degenerate. If you then introduce precession, like the binary black hole precession into this, then what you get is this blue set of data on the right. And then if you include, so not the aligned effect, just the precessing effect, you get the orange set. If you include both the precessing and the aligned components, you get the green curve. And so what we can see here is, looking at the plot for kappa 2, the thing that determines the magnitude of this quadrupole correction, we can see that the blue one isn't constrained. It's a uniform distribution. We can't really say anything about it. Now the orange and green curves, very, very similar. So this kind of tells us that most of our constraining power is coming from the precessing effect. And so here we've picked a system that has 50% mismatch coming from the aligned, 50% mismatch coming from the precessing part. So in terms of just the mismatch should be equal, but we can see from the constraining power, the precessing part is significantly more important to being able to constrain the quadrupole constant. Okay, so if we take this and apply it to several injected mass gap signals, I have 4 kind of cases on the right. So the first, a high spin black hole plus mass gap. The second, a more realistic spin black hole plus a mass gap object. And the second and third, the first object is in the mass gap and the second is a neutron star. Okay, so what we've shown here is that, for an A-sharp sensitivity network, we can maybe constrain this value to plus or minus 1. So for a mass gap object, you might expect this quadrupole constant to be somewhere between 2 and 3. So for A-sharp sensitivity, not really able to say anything with high statistical significance. Whereas we can see that when we move over to a cosmic explorer sensitivity, we can really pin down the value and we can actually tell the difference relatively easily between a black hole and something else. Okay. Now, moving on to a mass gap, or a black hole mimicker, sorry. We perform a similar analysis to that of the TGR papers, where both objects are assumed to have the same quadrupole constant. And what we've done here is we've rerun the analysis for 15, 12, 26 with the precessing effects included. And what we find here is that it improves the constraints, but not by a lot. And so for this particular event, we think that the logic is that the reason it doesn't improve the constraints a lot is because of the spin tilts. So if the spins are completely aligned, obviously there's going to be no precession. So you wouldn't be able to tell the difference there. But as it turns out, when the spins are in the orbital plane as well, the precessing effect also isn't informative. And that's because it scales with the projection of each of the spins onto the orbital angular momentum, which is going to be 0 for spin tilts that are in the orbital plane. Okay, so for this system, we wouldn't necessarily expect us to be able to constrain it that much. If we take a look at the same event, so we estimate the mass of the event, perform an injection with the same mass, same spin magnitudes, all the same, just different spin tilts. What we find is that the precessing effect is actually significantly more constraining. Okay. And so it's reasonable to assume that for some events in O4, the precessing effect is going to be significantly more constraining than the aligned effect. And so going into the future, we should be really considering this effect in future waveform models.
2 more minutes.
Okay. So just to wrap up, we have developed here a waveform model that is similar accuracy to others, but with this 10 times improved benchmark timing, as well as being able to include the effects of the quadrupole moment on the precessional dynamics, something that hasn't been done before except numerically. Here we do it semi-analytically, which is what allows us to get this speed up. And for mass gap objects, the spin-induced quadrupole moment turns out to just be kind of the best test as to the nature of the object. Now for black hole mimickers, it very much depends on your model of black hole mimickers. Some of them have huge tidal deformabilities, which are going to be easier to measure than the spin-induced quadrupole moment. But it seems like for black hole mimickers that are precessing, with this effect, we can provide tighter constraints than with just the aligned effect that was considered before. So again, going forward, we should start considering including this effect in waveforms.
Thank you very much. Okay, we have time for questions. Let's see. So we already have one question in the Q&A. See, Logan, do you want to unmute and ask it yourself, or do you want me to read it?
Yeah, sure. I can ask.
Okay.
Yeah. So when you talk about the 7 concept quantities for spinning binaries, right? So you said the magnitude of orbital angular momentum or the components of total angular momentum will be conserved, right?
Yeah.
As the system is emitting gravitational waves, it is losing orbital angular momentum. Mm-hmm. So, how do they remain conserved?
Okay, so I guess this point could be clearer. So because we're working with multi-scale analysis here, where you have these 3 distinct timescales, the orbital timescale, the precession timescale, and then the radiation reaction timescale. So the things that you're talking about, the magnitude of L and the components of J that change with time, those evolve on the radiation reaction timescale. So what's done is typically these things are assumed to be constant over the precession. You evolve the precession dynamics kind of instantaneously, and then you evolve these constants on the slow radiation reaction timescale. So in order to do that, you need a solution to the conservative dynamics in order to add that on top of the radiation reaction dynamics. And this is what's been done in the past to figure this out. So there, since we're dealing with the conservative dynamics and the solution to that problem, there L and J is conserved.
Yeah, just a follow-up. So is it always true, for all parameter space, that the precession timescale is always smaller than the reactive radiation reaction timescale?
Okay, yeah, so it depends on how close to merger you are, right? There's going to become a point where even the orbital timescale is the same as the radiation reaction timescale. And yeah, at that point, the three, you won't be able to model them as separate, but we found that, and in the past, it's been shown that up until, I forget what value the PM parameter, something like 0.4, this continues to work well. So yeah, typically so we just handle the inspiral part. And during that part, we find that, yeah, there's still this clear separation of timescales.
Thank you.
All right, other questions? All right, doesn't look like we have, Jocelyn, go ahead.
Hi, sorry, finding my Zoom buttons. I wanted to ask a little follow-up on the mass gap with next generation detectors slide. Just making sure I understood what type of objects are you assuming when you show these results? Like how are they things we expect to see, or I guess we don't have many observations?
So here we're kind of assuming that, because it's in the mass gap, the two options are black hole, which would have a quadrupole moment of 1, or some kind of neutron star. And if you look at it, as it turns out, in order to support the kind of masses that you would have in the mass gap, the thing has to be usually very highly spinning. And second of all, it has to have an equation of state that can support it being there in the first place, even if it's highly spinning. And so for the equations of state that can support objects in that region, you would expect the spin-induced quadrupole constant to be somewhere between like 2 and 3.
Okay. Are those disfavored by other current observations of 1708-17 per se?
So yeah, some of it is that other equations of states that where the quadrupole constant maybe plunges a little steeper. So you have kind of the left side, like the low mass side, that's constrained by these other events. And so as a result, just extrapolating out from there, there are only going to be some equations of state that can support this, right?
Okay. Thank you.
All right. All right, thank you, Michael. Let's move on to our next speaker. All right, so our next speaker is Lisa Drummond, and she will be talking about gyroscopes orbiting gargantuan black holes, incorporating secondary spin into extreme mass ratio in spiral waveforms.
Hi, sorry for the very long title. Okay, yes, I'm Lisa Drummond. I'm a PhD student at MIT, and I did all of this work in collaboration with my advisor, Scott Hughes, as well as my other collaborators who I've listed here. Okay. So I'm going to begin with just a brief introduction to extreme mass ratio inspirals, for those of you who don't think about them as much as maybe I do. So extreme mass ratio, exactly what you think they are. They're binary black hole systems where one of the black holes is much larger than the other. They have astrophysical significance because they're believed to be quite important and interesting sources for LISA, which is, as you all know, a future space-based gravitational wave detector. Also, they're quite interesting as a limit of the relativistic two-body problem, which can be solved very cleanly. And we hope that this limit can kind of shed light on the more general comparable mass two-body problem. Okay. So why is it hard to model MREs? So on the left, I have sort of your classic canonical comparable mass ratio waveform that you might see with sort of a binary black hole merger and LIGO. And then on the right, you can see an MRE waveform. And the first thing you'll notice is that there are hundreds and thousands of cycles. And also we have very disparate length scales. So you can imagine that if you try and treat this system using numerical relativity. You have to resolve all of those, integrate over all of those cycles, as well as resolve those very disparate length scales, which is very challenging. However, we're very fortunate in that this system can very conveniently be treated using perturbation theory, because of course you have these two very differently sized objects. And you can just imagine that the small black hole is essentially just a perturbation of the larger black hole's space-time metric. So you can essentially treat the small body as at 0th order just being a test body in the background space-time metric, and then you add subsequent perturbations to sort of correct that picture. Okay. So at the lowest order, the small black hole is just going to follow the geodesics of the background spacetime. So it's just going to travel along essentially Kerr geodesics. Of course, this isn't going to be quite enough for sort of LISA gravitational wave modeling. We want to be able to have more accurate waveforms than this. So we need to include post-geodesic effects, such as gravitational self-force, which, if you're not familiar with that, that is essentially the fact that the small body will itself curve spacetime, and this will then back react on its own motion. So that's self-force. But what about the spin of the black hole? This is also a very important effect. And when you have a small body with some spin, the sort of consequence is you get an effect called spin curvature coupling. And this is important to include because we expect astrophysical black holes will indeed have spin, of course. Okay. So this is, one of the few slides with equations. So I'll just step you through slowly. First of all, I'm solving these equations called the Matheson-Papapetrou-Dixon equations, which look at sort of a spinning test body in a background spacetime. I am taking the leading order in spin limit, which is okay to do in the extreme mass ratio limit. So basically what we have is this equation number 1. Hopefully you can see my cursor. This equation number 1 here, which describes the motion of the small body. And it's essentially this forcing term amounts to a coupling between the Riemann tensor of the background spacetime and the spin tensor of the small black hole. So here in my cartoon, I'm trying to sort of display this force. So you have the purple background spacetime of our very large supermassive black hole, for example, and then you have just a spinning top or gyroscope, which is essentially all we're considering the small black hole to be, just a spinning top. It's just some spin that's coupled to the background spacetime in a vacuum. Okay, and secondly, we have an equation for the evolution of the small body's spin. Okay, so at the very lowest order, the simplest thing we can possibly do, if we forget about radiation reaction, we forget about gravitational waves, and we just consider conservative orbits of the small body around a black hole. Obviously, we have the geodesic equations. That's the simplest thing we can do. Now, if we consider the small body to have some spin, then we use these Matheson-Papapetrou-Dixon equations that I've just introduced. And physically, what this means is that there's a coupling between the curvature and the small body spin, which leads to a force that pushes the small body away from a geodesic orbit. As I've said here, pushes the small body away, and it also causes the small body spin to precess as it orbits. Okay. Now, the second thing we need to compute is the radiation emitted by, a given orbit, right? So, or the gravitational radiation. So we can do this for sort of point particle or non-spinning bodies, and we can compute using the Tucholsky equation, the gravitational radiation corresponding to this orbit, and I've written the stress tensor for this point particle here. Okay, if we then consider the spinning body to be the source, then you'll have to include an additional term, which is the sort of the dipole term in this stress tensor. Okay. So what we do is we can take the sort of kinematics, so sort of a conservative orbit, sort of as a snapshot, and then we combine this with the gravitational radiation we compute, which allows us to evolve these orbits slowly. And combining all this information together, we can build an inspiral. So the full case that includes the spin of the small black hole, the spin of the secondary, we would use the Matheson-Papacho-Dixon equations to include spin curvature force and the kinematics. We would also compute the gravitational wave fluxes for a spinning body by including the dipole term in the stress energy tensor, as I mentioned. And this is what we've done in a paper with myself and my advisor and some collaborators. However, combining these things together and computing the generic inspiral for spinning bodies on generic orbits is work in progress. So there are some sort of technical and conceptual challenges which need to be overcome. So as an intermediate step, what we have done is to consider sort of spinning body kinematics combined with point particle gravitational wave fluxes as a way to sort of look at an intermediate step before we consider the full picture. We just want to see what this particular contribution from the spinning secondary will, what effect it'll have on the waveform essentially. Okay. So I've sort of already said this, but basically our motivation is to incorporate some spinning secondary effects into generic waveforms. And this is an intermediate step on the path to including all of the effects. It's also interesting because we're sort of isolating the conservative sector and seeing its effect individually. And also the formulation, which I'll describe in the next few slides, has the benefit that it will interface hopefully immediately with existing frameworks for sort of for modeling self-force and stuff like this. Okay. Okay. So the approach we use is a very old one. It's something which has been done for Keplerian orbits in Newtonian gravity. It's oscillating elements or oscillating geodesics in this case. So essentially, what we want to do is we want to consider a geodesic orbit, which is parameterized by some orbital parameters, which are constant in time. So it could be energy, angular momentum, and the Carter constant, or it could be sort of orbital elements such as semilattice rectum, eccentricity, and the cosine of the inclination angle. So that's what this PEX is here. Then what happens is, as the system emits gravitational waves, the orbit will evolve very slowly through a sequence of these geodesic orbits, and you build an inspiral in this way. So each of these orbital parameters is now a function of time. We promote them to sort of time varying quantities. Okay, so here's sort of our schematic of our equations. We have this P vector, which is the P, E, and X, the orbital elements. We have the Q, which are the phases. And at a geodesic level, we'll just have essentially the P's will be non-varying because they're constants. Then as we consider a post-geodesic effect, we'll have this forcing term and also corrections to the frequencies, which will help us build our inspiral. Okay, so if we just include these sort of adiabatic gravitational wave fluxes, we get an inspiral which looks like this. So it's evolving in this semilattice rectum eccentricity inclination space, and you can see it sort of starting with this eccentricity, evolving, and then the eccentricity ticks up sort of in the very deep in the strong field towards the last stable orbit. If we include spin curvature force, these are the oscillations that you see. But you'll notice that essentially, because spin curvature force is just a conservative forcing term, On average, the evolution of the orbital elements does not change. However, there will be a correction to the phases. So there will be a dephasing of the gravitational wave due to the presence of spin curvature force. Okay. So what you'll notice is that you have all of these very small, so what I'm plotting here is the dephasing in the axial coordinate. So this will be sort of roughly corresponding to the dephasing you see in a gravitational wave, roughly. And on the bottom axis is time, of course. So this is the amount the gravitational wave is dephasing due to the presence of the spin of the secondary black hole. And you'll notice that there are lots of oscillations here. This is annoying because we have to integrate all of these and resolve them as we integrate. And ideally, we want to be able to compute many, many inspirals across the entire parameter space. So we want to speed this up. We do this using something called a near identity transformation. So we essentially define this transformation and, and then we solve the new equations, basically removing these oscillations, and we can solve these equations much faster. So there'll be a 2 to 5 order magnitude speed up, and we can directly use these phases that we solve for as inputs for generating our waveforms. And if I haven't really discussed this in any great detail, I've had to gloss over all of the technical things. So this is work done in collaboration with Philip Lynch. So please check out his papers if you're interested. Okay, so finally, this is a waveform for an equatorial orbit with aligned spins. And you can see, I'm just showing here at the end that there's a dephasing between the spinning and the non-spinning case. And again, I want to emphasize, this includes one part of the contribution from the spinning secondary, but there is still another contribution from the dipole term in the Tucholsky source. Okay. So,
sorry, one more minute, sorry, two more minutes?
Yes, perfect. Okay, so finally, I just wanted to show you, we've also done this for fully generic waveforms, so arbitrary inclination and eccentricity with, in principle, arbitrary alignment of the spins, although here I'm showing the aligned case, but yeah. Okay, so to conclude, we've computed these fully generic inspirals and waveforms with arbitrary spin alignment and spin precession, but there are some missing elements which need to be included to build the full picture. So the natural next steps are, of course, to include these missing elements, but there are some sort of technical and mathematical challenges, as I mentioned, for doing this. So one of the interesting questions which can be answered here is whether this dephasing is detectable or not. So there have been some analyses showing that, for example, for like circular equatorial orbits, the spin of the secondary isn't necessarily detectable, but this is likely due to degeneracies, sort of a similar nature that Michael discussed in his talk. So in principle, if you look at sort of more generic cases with precessing spin, the spin of the secondary is likely to be, or potentially could be, much more detectable and important. So we need to investigate this. And with that, I'll conclude. Thank you so much.
Thank you. All right, we have time for questions. You can put your, you can raise your hand if you have a question. You can also put it in the Q&A. Okay, I don't see any questions right now, so I guess I'll use the chair's prerogative to ask a question. Yeah, so so in terms of detectability, do you have a method in mind for how you would assess whether these effects are detectable?
So it's going to be a challenge because basically it takes us a while to compute a waveform for a single set of parameters. So in principle, what you'd want to do is build secondary spin into something like the fast Emery waveform package, which uses like GPU acceleration and clever tricks to speed up the computation of a single waveform, so you can do easily search over the whole parameter space and do like a nice Bayesian analysis. We could use Fisher matrices, for example, which are usually a little computationally cheaper. Yeah, so this is something which I haven't thought about in great detail, but there are going to be some computational challenges to overcome in order to do a thorough analysis across parameter space. Does that answer your question?
Yes, thank you. Other questions? All right. Well, thank you for a very nice talk, and thank you to the 3 speakers we've already had. We're going to take a break, and then we're going to start with the next talk, Jocelyn Read, at 10 minutes past the hour. So everyone can kind of, get a drink, stretch their legs, whatever, and we'll be back in about 10 minutes. All right, thank you, everyone. Our next speaker is Jocelyn Read, and she will be talking about quantifying and interpreting gravitational waveform error.
Okay, thank you everyone for sticking around for this this piece of the talk. I'm going to be talking through some of the results in a recent paper with the archive code there that was published in Classical and Quantum Gravity. And to start things off, one of the motivations of this was looking at some previous literature from Bruce Edelman and collaborators looking at unmodeled physics in gravitational wave observations and how that could be constrained in a generic way. So Edelman et al. Look for coherent support in gravitational wave data for some sort of departure from the waveform model used in the parameter estimation of gravitational wave inference. So to do this, the idea is that you use some sort of spline description for a very flexible model for changes in the amplitude and the phase of the actual gravitational wave strain signal. This is similar to what's done for calibration marginalization or calibration recovery. And they recover these 1 sigma and 2 sigma contours seen here on the left, which are more or less compatible with the no departures from the waveform model used in parameter estimation, although there's sort of this potentially interesting excursion right around 60 hertz. So I'm not taking this as something that I'm considering a significant result, since that's sort of the power line frequency. But I want to look here in how we can astrophysically interpret generic signal difference results like these, and also compare generic differences between the waveform models of different families that we use to describe gravitational wave sources. So that's the story here today. So to set up for this, I'm gonna set the stage by connecting how we describe our source modeling, which is generally with some sort of multipole expansion in spherical harmonics of the 2 polarizations of the gravitational waves going out in an angular-dependent pattern away from our source. For what I'll look at here, I'm assuming the source is emitting in a very quadruple dominant way. This is very appropriate for near equal mass systems like most neutron star binaries. But in the literature, including actually in a lot of the literature for LISA type sources, there's a lot of exploration of how to handle this type of analysis with higher multiples. The gravitational wave source strain is projected from this plus and cross polarization onto the detector in a way that depends on where the source is in the sky and how it's oriented. And we end up with a measured strain amplitude in each detector, which has some sky location, orientation, inclination terms, which sort of are a prefactor on the amplitude of the gravitational wave. And then these sort of intrinsic properties that are coming from our original quadrupole mode of the source emission, this amplitude and phase in the source frame. So this is sort of the framework I'm going to talk about when linking what we observe in the detector and what it means for the sources that emitted that particular gravitational wave. So the key hook for understanding how to interpret these types of signals here, I'm going to use the decomposition of our time domain to define an instantaneous frequency. So this is a very standard thing to do from the phase derivative in the time domain. And once you do this, many of our signal models that go into the Fourier domain assume what's called the stationary phase approximation, where the primary driver of our signal at a Fourier frequency, little f here, comes from the part of the waveform where the source frequency is at that same frequency, as at the big F is at the same value. And we can write the signal amplitude and phase in the Fourier domain in terms of the time domain amplitude and what I'm going to call f dot later in this sort of description, which is the time derivative of the frequency of this time domain signal. All the intrinsic physics now is encoded in these two functions of the instantaneous frequency. So the masses, the spins, the tides, the couplings between all those. And then this is integrated twice to give us sort of the time piece and the phase piece that you might be used to seeing if you're familiar with the stationary phase approximation. And then we also get out these phase and time constants of integration, which emerge from this double integral and tell us where in time the signal arrives in the detector and what phase it happens to be oriented at when that happens. So these are sort of signal-specific quantities of a particular arrival and orientation, more extrinsic properties of the signal again, and all the source physics is in this time domain amplitude and this frequency derivative. So this lets us set up to ask the question of what are the real waveform differences of the predictions of two models. Here's an example with binary neutron star comparisons. On the right, there's this amplitude, which is increasing in frequency. Time domain amplitude increases as the stars get closer together. And on the left, we have this frequency derivative. If you're coming from the numerical relativity community, this is often talked about in terms of the orbital angular frequency derivative. They're proportional to each other, so this gives us a way of comparing the dynamics of different waveform models directly from the signal description in a way that's independent of the particular arrival time and phase reference of an individual component. So here I have a bunch of these semi-analytic models on the left compared to a binary black hole, which is in green. And you can see all our tidal models depart. They have a more rapid increase in frequency as the stars go closer together, which agrees also with the numerical relativity simulation at two different resolutions of the same source properties. So we're seeing sort of some differences in the waveforms coming from the different physics. And this is sort of my favorite example of physical impact to look at. It translates then into what we measure in terms of a residual phase. So this is sort of what we can think of in terms of the phase differences that remain between two waveform models. And one note is that if you start at, say, these two numerical simulations here are aligned at one particular point frequency and then depart away from that. But really, if you're trying to consider what might be observable, you want to think about what's left over after arbitrary marginal shifts in time and phase, after marginalizing over the arrival time and phase parameters. So what I'm showing here is for these family of waveform models, the residual phase difference after a maximum likelihood fit of these two reference parameters, time shift and phase shift. This is done here with a linear regression weighted by the variance you expect for a given power spectral density, given a particular waveform amplitude, which sort of leads to a way to compare phase differences as a function of frequency to the expected noise fluctuations as a function of frequency in the detector through a condition based on characteristic strain. So characteristic strain is usually what we compare the power spectral density of interferometer noise to. When we look at, say, the waveform amplitude, we plot the characteristic strain, and you would consider something arising above the noise if the characteristic strain at a given frequency is higher than the PSD. So this same condition can be mapped onto phase differences. So you can look at how, for example, for 1708-17, phase differences that were within this shaded region would be obscured statistically by the fluctuations of noise in the interferometer. Okay, so this is just the framework connecting the source physics to the phase impact in a way that lets you also look at statistical and systematic uncertainties. So one of the other things you can do with this kind of comparison is think about how the goals for amplitude and phase uncertainty that would be required for future detectors to satisfy this characteristic strain condition I just discussed. So while I was talking before about waveform model uncertainty, this is actually not specific to modeling coming from our source model. It can also come from uncertainty in our detector model. So in general, when we're trying to understand systematic uncertainties in our waveform or detector model, we know that there's some true waveform or some true strain that the detector is recording from. And then our model, our output channel or our modeled waveform has some potential range of uncertainties coming from amplitude and phase fluctuations that are not well expressed or have some uncertainty in them. If you take this characteristic strain above detector noise implied for the difference between the true strain and the modeled strain in either of these cases, you can get a goal, for example, for what a 100 megaparsec binary neutron star would need in terms of calibration and waveform accuracy for amplitude and phase differences, frequency by frequency, coming from the PSD of the detector and the expected amplitude of the signal. So this tells us, for example, that, well, a 1% accuracy, calibration accuracy would be sufficient for pretty much advanced LIGO plus type binary neutron star signals. It would be a limiting factor if we were going to try and take full advantage of all the potential promised by the power spectral density projections of something like Cosmic Explorer. So being able to flexibly model and understand waveform uncertainty is going to be important, as well as calibration uncertainty is going to be important for making the best use of next generation facilities. This is sort of an alternative way to assess waveform impacts compared to something like mismatch. Mismatch is basically an integrated quantity across frequencies. This is looking at the integrand of the mismatch calculation and seeing how whether or not it's above the noise expectations or below the noise expectations, frequency by frequency.
2 minutes.
So the last thing that I did in this paper is coming from mapping those characteristic functions to an energetics interpretation. So the amplitude of the time domain waveform can be directly linked to the luminosity. So the gravitational waves are carrying away energy from the system. So in an oscillatory wave emission, you can link the amplitude of the wave to the luminosity, or the energy carried by the wave, well, amplitude squared. Similarly, when we're using an energy balance interpretation for how the waveform moves through its orbits, if we're doing this kind of adiabatic evolution type picture, you can interpret this F dot as a balance between the luminosity, the energy that's emitted, and how the energy of the system changes with the frequency of emission. So this is the derivative with the emission frequency of the energy of the system. So this is just slightly different tweak of how we usually write the energy balance in, say, a post-Newtonian framework. This energetics lets us interpret variation of any of these luminosity or energy functions, including something like additional luminosity from non-gravitational wave effects. So if you have a multi-messenger signal that loses significant energy to other forms of, say, light or neutrinos, or numerical relativity models that have unphysical dissipation, that would be a non-gravitational wave energy loss. You could also have internal energy transfers, such as resonant modes, dynamic or adiabatic energy transfers that change the way that the energy changes with frequency. So if these are small corrections, you can propagate them through the stationary phase approximation to the time domain and get a map to the implied amplitude and phase corrections that correspond to a given energetics. So the capstone of the initial slide showing these flexible waveform constraints is that you can interpret something like that phase shift as being compatible with a resonant energy transfer at 60 hertz of the gravitational wave emission frequency of some relative fraction of the orbital energy. So generically, we can potentially use results like those of Edelman et al. To limit unmodeled energy transfers of any type that are not in the waveform family used for analysis. Another application of this framework that we'd like to do is to marginalize over uncertainties in our waveform modeling when inferring the source properties. I will stop there. I have a lot of backup slides that I won't get into, but I'm happy to answer any questions.
Thank you. All right, we have time for questions. All right, I don't see any raised hands or questions in the Q&A yet, so I will ask the first question. Yeah, so what do you think are the challenges for having accurate waveforms for next generation ground-based detectors?
So I think one of the things that this comparison illuminated for me was that our current semi-analytic models are not taking advantage of the capabilities of numerical relativity to understand what's going on as we move into the merger. So these two resolutions here for the simulation results show very good agreement with each other at high frequency, including through the merger regime and into actually the start of the post-merger. So we actually have good coherent understanding of the source dynamics there. And then you can see these semi-analytic models don't actually do a great job of tracking that right now. So we have some unexplored potential at the highest frequencies to better match our waveform framework to the numerical simulation data that exists already. The other way to improve our waveform construction might be to move away from using time slides, shifting in time and frequency and phase before we kind of construct our models for long waveforms, and to something that is more unified in the way we try and describe the waveform model from the source physics. So those are sort of two directions that I think would be helpful in moving the waveform error down. But actually calibration uncertainty is going to likely be the limiting factor below sort of 100 hertz, hundreds of hertz even, for binary neutron stars.
Thank you. Any other questions? All right, if not, thank you. And let's move into the final speaker of this. So we're gonna have one more speaker, then a 10-minute break, and then another speaker. So the next speaker is, oops, hang on a second. All right, the next speaker is Adam Solomon. All right, so our speaker is Adam Solomon, and he will be telling us about love numbers and hidden symmetries of gravity.
Great. Thanks, Sarah, and thanks to the organizers for letting me talk. So I want to talk about love numbers of black holes, which are tidal deformability coefficients, and what they can tell us about the nature of gravity, and in particular, its symmetries. This is work I did with some excellent collaborators in these archive papers listed there. The motivation, I think, is really nicely summarized by this quote from Chandrasekhar. Black holes are, which we're now observing in binary mergers, are pure gravity, they're pure space-time. And so by understanding their properties, we understand something about gravity itself, not just about the stuff that's gravitating. When we're looking at gravitational waveforms, what we're really doing is studying the two-body problem in GR, which is hard. So it's common to split it up into these three customary phases, where it starts off very similar to the two-body problem in Newtonian gravity, just circular orbits. That has a quadrupole, which means that it's going to source gravitational radiation, which means that because gravitational waves carry energy, the orbit's going to start to lose energy to gravitational radiation, start decaying. Eventually, you'll get into this highly nonlinear phase where the fact that GR is nonlinear takes over, and then they merge into a single object, and it rings down. And each of those three stages involve very different tools. So I'll be focusing on the inspiral in this talk, but then, during the merger, you really need numerical GR. And the ring down, as we've heard in other talks of the session, is very nicely described by black hole perturbation theory and the many tools in there. So let's look at the inspiral. The point of the inspiral is that we can calculate it using, there's a lot of different small expansion parameters that are available to us to try to calculate what the waveform is. And for modern gravitational wave astronomy, we need these to really high orders now with these expansions. But basically the different types of expansions that could be at play or that are at play in the inspiral, there's the post-Newtonian expansion, which is in the orbital speeds in units of the speed of light. There's perturbation theory, which is equivalent to an expansion in G Newton, a post-Minkowski expansion. And you can also expand in the sizes of the objects divided by their the orbital size. And then you can actually use effective field theory techniques where, as I'll describe, you treat the objects that are orbiting each other as point particles, and then any corrections due to their finite size and structure get encoded in higher order operators, whose coefficients are called Wilson coefficients. And we'll see that those are precisely the tidal love numbers that we're interested in this talk. So what are the love numbers? Well, they're defined initially in the Newtonian context. There's a guy named Love who lived about 100 years ago and defined these, and they have to do with if I have a gravitating body and it has some external tidal field. So if I focus on one of the objects in a compact object binary, and imagine that the faraway companion is sourcing some tidal field that's going to deform it, the amount that it deforms based on that applied tidal field, external tidal field, is going to be based on its internal structure, So, if you have a very stiff object, stiff equation of state of a neutron star versus a very not stiff one, you'll have less or more deformability given the same applied external field. So these are really interesting, for instance, for measuring the internal structure of neutron stars, the neutron star equation of state. And these are observable, at least in principle, and certainly coming up in the future. They tend to impact the waveform at the 5th post-Newtonian order, which is high, but is within reach. So during the inspiral, it's convenient to expand, like I was saying, to make use of the fact that the size of the objects or compact objects are very small during this phase compared to the orbital separation, and that the orbital velocities are small compared to light, and so everything's very adiabatic and effectively static. So to leading order, we can, in the EFT context, what we do is we write down an action for the particle that starts off just by saying it's a point particle, just as the usual point particle action. And so in this approximation, the two objects are orbiting on geodesics in each other's spacetimes. And then the fact that these are not quite point particles, but they actually have some size, some structure, will affect the inspiral in small ways that can be encoded in a kind of general way using the rules of effective field theory. So using the symmetries and fields available to organize these corrections. And these coefficients, CE and CB, which come in front of, these are the electric and magnetic parts of the Weil tensor squared. These Wilson coefficients are precisely the Algasian variant definition of these Newtonian love numbers, or a gauge extension of them to GR. Now, by the usual sort of naturalness logic of EFT, you write down all the operators you're allowed to, consistent with your symmetries, and the coefficients are order 1 in some, when they're dimensionless. And so a dimensional analysis estimate for that should give you that these love numbers are generally going to be some order 1 constant times RS to the 5th over G Newton. And that's borne out for neutron stars. But for black holes, that naturalness expectation fails. The love numbers turn out to be 0, as I'll discuss again in a couple of slides. But by the usual EFT logic, this is kind of mysterious because it signals the presence of a hidden symmetry. Otherwise, it would be a kind of classical fine-tuning, analogous to like the Higgs problem, the Higgs hierarchy problem, the CC problem, that sort of thing. Okay, so to show you what I mean by the love numbers being 0 and a little more about how to calculate them, I'll need a one-slide version of black hole perturbation theory. We'll get through it really quickly. So for Schwarzschild, we can do normal metric perturbation theory. We can expand the metric into the background Schwarzschild metric plus some perturbations, separate those perturbations, and then from the components of the metric perturbation and its derivatives, you build up these master variables called the Regge-Wheeler and Zerilli variables, and they satisfy master equations that are Schrodinger-like equations called the Regge-Wheeler and Zerilli equations. So that encodes the dynamics of gravity linearized on a Schwarzschild background. On Kerr, things aren't quite so simple. The metric perturbations are inseparable. And so what you consider instead are wave equations for the Weil tensor projected along certain directions. And that gives you what's called the Tucholsky equation. And what's nice about the Tucholsky equation, it actually unifies spin 0, spin 1, and spin 2, and even spin 1/2 for neutrinos. And we'll see that for the static solution that we're interested in, that all of these spins are related to each other and sort of behave the same. So now let's look at how these love numbers are calculated. So we'll take, just for simplicity, the Regge-Wheeler equation for odd parity metric perturbations. So it's got this nice little Schrodinger form where its derivatives with respect to this torus coordinate, and it lives in its potential V minus, which I don't think I plotted, but it's a potential. And so this, so now you want to look for solutions to this equation that obey the boundary conditions that are physical. And so again, the situation we're imagining here is that I'm zooming in on one of the objects, one of the black holes, in this case, in the binary. And then far off, as what we're calling infinity, would be its binary companion, and it's moving so slowly that we're going to take the everything to be static to leading order. So that's why we're going to solve these equations with zero frequency. And so the Reggie-Wheeler equation becomes a hypergeometric equation, and you can expand it at the horizon at infinity, where you set boundary conditions, and get simple scaling behaviors. So near the horizon, there's a constant mode for this Reggie-Wheeler variable, and there's a mode that diverges logarithmically as you approach the horizon. And then at infinity, you have solutions that are power laws in R. They depend on the angular momentum of the spherical harmonic. And so you have a growing mode, R to the L, and a decaying mode is 1 over R to the L plus 1. We interpret the growing mode as being imposed when you impose the boundary condition. The growing mode for each of these spherical harmonics contains the tidal field that you're applying. And then the decaying terms correspond to a static response. So algorithmically, just what we're going to do is we're going to set at the horizon, we're going to demand that this divergent piece not be there, because if we're looking at black holes rather than neutron stars or other objects where the horizon isn't there's an actual surface where you put boundary conditions. For the black hole, you're going to put the boundary conditions at the horizon. And so this divergent piece can't be physical. And so all you want to do now is take the solution to this equation that's regular at the horizon, expand it at infinity as a superposition of growing and decaying modes, and read off the coefficient of the decaying mode. That gives you the love number. But what turns out for this equation and for other massless field equations on black hole backgrounds, the regular at the horizon solution corresponds only to this growing mode at infinity. Kind of similar in essence to the no-hair theorems too. Basically, so that's the statement that black holes have no love number. And I've shown this for Schwarzschild perturbations, but it's been proven for Kerr. In Kerr, there's a dissipative piece, but the conservative part, which you call the love number, is vanishing. So in the last few minutes here, I'll tell you about one symmetry that's been suggested by us to understand why this is. And instead of dealing with gravitational perturbations, let's just look at the Klein-Gordon equation on Kerr, say, or on Schwarzschild. And we'll set time derivatives to 0. And so it ends up taking this form in terms of this Hamiltonian H. And it turns out that this equation of motion admits raising and lowering operators, which raise and lower L by a step. And so it takes a solution with 1L, and you can get another solution at a higher or lower L. If you combine that with an accidental symmetry that exists at the lowest level, so that's L equals 0 for scalar, L equals 2 for gravity, then you can do this thing where you say, okay, I'm going to say it's some fixed L. I can use my lowering operators to go all the way to the bottom rung of this ladder, apply this accidental symmetry, go back up, and then I've got a symmetry operator, written it here, which acts on a mode of an L mode, a solution to the level L equation of motion, returns another solution to that equation of motion. So since that's a symmetry of the action, we can use the usual Noether argument to derive a conserved charge. In fact, those charges are nothing other than the love numbers. And what you can do is very simply evaluate the charge at the horizon, applying this no diverging term boundary condition. You find that it's 0, go off to infinity, read it off there, and you find that having this charge be 0 tells you that the love numbers have to vanish. I showed you that for a spin 0 field. You can do the same thing for the Reggie-Wheeler or Tucholsky equations. Or, quite interestingly, you could, there's a ladder in spin. There are ladder operators for 0 frequency, which allow you to take a spin 0 or spin 1 or spin 2 solution, map them to each other. And so the proof I just showed you for the vanishing scalar love of the Klein-Gordon equation also works, applies to gravity through this. Why do these ladder symmetries exist? There's a nice geometric origin for it, which is that if we look at the static Klein-Gordon equation on Schwarzschild, you can think of it as living in an effective metric, as in the equation of motion for a field on this metric is going to reproduce the static Klein-Gordon equation on Schwarzschild. And then there's a simple conformal transformation you can do, which maps this to a massive scalar on what ends up being a Euclidean ADS3. And so the symmetries of Euclidean ADS3, which are 6 Killing vectors, are going to give you symmetries. They're going to be conformal Killing vectors of this original metric, and they're going to give you symmetries of the scalar. And in fact, one of them, I've written it down here explicitly, so this is one of these Killing vectors of this ADS3.
Excuse me, you have got 1 more minute.
Great. So if you act the symmetry on one multipole mode, it actually spits out one lower and one higher with these raising lowering operators acting on them. So that's what's underlying this structure. You can also see this conformal symmetry interpretation of these ladder operators beyond the exact static limit, where there's this very beautiful SO42 invariance with a lot of symmetry in it. And a brief slide on higher dimensions, which I won't get into the details of. And I'll put my summary up here. So love numbers are really interesting. They're receiving a lot of attention for a reason. They're observable in waveforms. And the prediction that they vanish for black holes in GR is pretty firm. They give you a test of things like the Noether principle of the symmetries of gravity. And so, they point the way to hidden symmetry structures in black hole perturbation theory, which I think still need to be explored. Thanks.
All right, thank you. All right, do we have questions? I don't see any questions in the chat or in the Q&A. Jocelyn, go ahead.
Hi. Yeah. So this might be a bit of a naive question, but I'm trying to understand this ladder symmetry argument a little bit. And when you say that is there any sort of physical interpretation in GR of what that symmetry means that would help us understand why it could be linked to like a tidal coefficient type thing, or is this something that you've thought about?
It's a good question. Let's see. So if you want like a deep reason, I'm not sure I have one for you. It's something I'm definitely, we're thinking a lot about, what is this sort of fundamental? Is it, is it one of these magic properties like the Killing tensor that we have, for example, for Kerr, or, there seems to be extra symmetry in the static case, so it's actually a little more intricate than that. I would also say that this story does exist. So I cite this paper by Compton and Morrison, who do a very similar thing on de Sitter space, that in light of this stuff I'm saying here about this effective ADS, actually turns to be exactly our story by a conformal transformation and analytic continuation. And so there, the thing that they're explaining with this symmetry is the fact that de Sitter space is transparent in odd dimensions. Seems very different than tidal. So I wish I had a better answer for you, but I think there's something still quite serious about all this.
Not at all, but is there a reason to expect there would be a physical interpretation?
I don't see why not. I think, I think the Kerr black hole is very special in a lot of ways, and clearly that specialness is going to impact on the perturbation theory, but the link between those is a little bit obscure sometimes.
Thank you.
Thank you. I will ask a question. This might be a naive question. I'm not familiar with, thinking about love numbers for black holes. And so I was wondering whether you've thought about connecting these symmetries to some of the other ways that people describe symmetries of Kerr, things like the Garish-Hansen moments, the no-hair theorem, written in terms of mass and spin moments, for example, or if you think that's possible.
Yeah, I'm sure it's possible. There's definitely a relation. We pointed out in one of our papers, that's going to be this 2105 paper. We actually point out an explicit link between our symmetries and the sort of linear version of the no-hair theorem, but also the no-hair theorem, it goes way beyond linear perturbation theory. And so it's more of an overlap, right, than an explanation. Yeah, that's what I say. Yeah.
Okay, thank you. All right, so that takes us to the end of the talks in this session. So we'll have a 10-minute break, and then we have one more talk in the modeling gravitational waves session. And so we will come back at, sorry, I don't know what it is in UTC. We will come back in 10 minutes. All right, let's go ahead and get started with the final talk. Okay, so our final talk about modeling gravitational waves is from Subhajit Dandavat, and he will be talking about characterizing bursts with linear memory events with LVK and PTA observatories.
Yeah, thank you very much. So myself Subhajit. So I'm a PhD student at Tata Institute of Fundamental Research, Mumbai. So today I'll be talking about characterizing the burst with linear memory events with LVK and PTA observatories. And this is in collaboration with the following colleagues from TIFR, LIGO, and the Indian Pulsar Timing Array, and the IPT, International Pulsar Timing Array. So this is our very recent publication, and where we have modeled the burst with linear memory that originates from the hyperbolic encounters of black hole. We have modeled this on the post-Newtonian accurate hyperbolic orbit, and then I will describe the salient features of this publication, and I'll be discussing about the possible ongoing searches, possible ongoing injection studies and searches, both on the LVK and the PTA, simulated LVK and PTA dataset. So this is where I have described the two hyperbolic encounters of the two black hole, and with the following configuration. And here the total mass. This scenario is with the total mass of 40 solar mass and the eccentricity of 1.1 and the impact parameter of 50 gm/c². And this is the orbit. And you can see the difference between the and this is, by the way, this is plotted in the center of mass frame of the center of mass frame of the one black hole, and the reduced mass is orbiting of the around the center of mass. And you can see the difference between the Newtonian and the third post-Newtonian accurate hyperbolic orbit. So in the third 3pn orbit, we have the one turnover, and this is how the H plus and H cross plots looks like. So in case of H plus, so we have the burst, and in case of H cross, we have the burst as well as the linear memory event. And by memory, that what I mean to say that so the waveform does not get back to the original position, and so even after the encounter. So whenever you have the memory, you have the positive deviation in the delta H plus or H cross. So we have developed a LAL-compatible hyperbolic TD for LVK and an enterprise-compatible GW-High for the IPTA to search for the burst with linear memory event with the black hole. So in order to do so, we will employ the post-Newtonian approximation. So when we are talking about the NPN order correction to the Newtonian gravity, that means V/c² to the power 2n or Gm/r² to the power 2n correction and to the Newtonian GR. So in order to tackle this such kind of problem, we need to first solve the p-n accurate orbital dynamics, and then you need to solve for the polarization state. So this is the flowchart for the post-Newtonian description for all of these parameters. This is for the orbit, and this is for the polarization state. So what we will be using, the post-Newtonian will be using the quadrupolar accurate H plus and H cross, but the orbit will be taking to be fully 3p accurate, which incorporates both the conservative as well as the reactive contributions, which comes as 2.5p in order. So this is how our orbital parameterization looks like. So the incorporation of the post-Newtonian approximation, and it includes the three eccentricities. So this is ER, ET, and E5. So here U, unlike the eccentric cases, here U is just a parameterization, and this N and this L is the mean anomaly. It can be thought as the area. It is proportional to the total area squared by the radius vector, as described in this figure. And this N, it can be thought as like the inverse of the time span of the observation. So the physical quantities to observe here are the velocity at infinity, and then let's say the mean anomaly, and the eccentricities, and another one is the impact parameter. So this is the flow chart how we construct the H plus and H cross. So we'll start with this H plus and H cross as a function of R dot phi phi dot. Then we will incorporate this 3p accurate expression for the R dot phi phi dot into the H plus and H cross. Then we'll incorporate also the Nicolas method to invert the mean anomaly into the U, or the whatever I have introduced earlier. And then and finally we will impose the gravitational wave polarization, gravitational wave. So that we will incorporate the radiation reaction terms into account to solve, and basically we'll be solving for the three coupled differential equation for this du by dt, dn by dt, and d by dt. And finally we'll incorporate the effect of the gravitational wave on the system, that is that in the observer the radiation reaction terms, to get this our H plus and H cross so in the 3p accurate hyperbolic orbit. So this is implemented in LAR in the neighbor of hyperbolic TD, and this is how it can be called using the Renormant pi-security package. So we have also made this enterprise, made an enterprise compatible package, that is GW-Hive. In order to do so, what we need to do, we need to do a additional integration over the H plus and H cross. So in this case, there is no contribution for the Pulsar term, because the where the Pulsar term contributes, or the regime where the Pulsar term contributes, in there the waveform is essentially 0. So and we will use slightly different parameterization for the search purposes. So we'll break this timing residual into two parts. One incorporates the amplitude, and one incorporates the phase part. So this is the order one quantity. This phase part is the order one quantity. And this amplitude is basically the amplitude of the timing residual. So using this hyperbolic TD, we have also computed the further luminosity distance, or the horizon distance, and such that such an event can be seen up to optimal filter listener of 8 for Einstein telescope and LIGO. So from this picture, this is plotted with the fixed eccentricities, but all the four plots are with the variable impact parameter and the variable masses. So with this restriction that R minimum, the distance of minimum approach is at least 10 gm by c square. With this restriction, and it can be seen that such an event and can be seen for LI for the advanced LIGO, for the binary neutron star system for 20 megaparsec, and for the binary black hole system up to 170 megaparsec, and for the same for ET is Einstein telescope is 260 megaparsec and 1.9 gigaparsec. So, and these are our ongoing effort to search for the burst with linear memory event for the PTA dataset. So this is mainly in collaboration with the Wimonu and Loki. So, so this is how the timing residual looks like for the following configuration in case of PTA dataset. So here I have taken the total mass of 10 to the power 10 and the impact parameter of 70 gm by c square, an eccentricity of 1.1, and it is important thing to note that such an event with the distance of 1.6 gigaparsec, I am still getting a timing residual of 40 in the order of 40 nanoseconds, and so it means such an event can be seen up to such large distances of 1.6 gigaparsec, and so if you make a all sky search, so this is how the quadrupolar pattern of the source has been it can be obtained. So, but this is actually computationally expensive because you need to do additional integration over the time. So in order to optimize this, what we have done, so we have derived the semi-analytic expression for the timing residual under the PN consideration. So basically we have considered the slow advance of periapsis, and then if we expand our phase into the two, if we take our phase into the two part, that is phi equals to omega plus p, and then if we after taking into the consideration of the slow advance of periapsis, we can able to express our S plus and S cross, that is the integral of the timing residual with respect to time, with integral of the waveform with respect to time. So with this following form, and it can be verified that this H plus and H cross it obtains this it obeys this relation. So with this we got around the 200x improvement in the computational performance, and this would allow the efficient search for the search given in the PTA dataset. And this is how there are the difference between the actual analytic template and the numerical templates looks like. So this left plot is for the S plus, and the right plot is for the S cross. So you can see, and so here in the you can see the difference is at least one order below the actual values. So here, but for the low eccentricities and the for the high eccentricities and the impact parameters, the high eccentricities and the low impact parameter, the differences is higher. So we still need to investigate such scenario. Still, we are improving the templates, our analytical templates. So this is our improvement factor as a function of eccentricities, and this is the we have also plotted the mismatch as a function of eccentricities. So you can see that for lower eccentricities the mismatch is higher, so it is even going bad up to like this value 10 power minus 1 or so. But after let's say eccentricities of 1.3, it got stabilized. So yeah. So with this analytical template, actually we did a single pulsar injection on the nanograph 12.5 year dataset. So with this J0030 plus 0451, and with the we have injected the white noise plus red noise plus our signal, but we only search for the red noise along with the hyperbolic model parameters. So this is the recovery we obtained. So it is so here you can see that so the E naught, so the hyperbolic eccentricities, it is not recovered correctly. So even so now for this next goal, so also we have taken a 25 nanograph pulsar of dropout factor close to 1 from this paper. And then we did the injection on the injection with only with the white noise parameters and our signal, and we search for all of the parameters for our model, and this is the recovery we obtained. And you can see the recovery for some of the parameters, they are not good. So this is because like this such kind of signals, they contains only one cycle, and with one cycle it is not expected to get a good recovery for all of the parameters due to the less information in the signal. So this yeah. So we are also doing the injection studies in the ground-based observatories or the in case of injected in case of LIGO-Virgo-KAGRA dataset. So this is and this is if we so here this is with the zero noise injection, and but so if I on so this is our injected parameters of mass equals to 60 and B equals to 60, gm by c square equals to 1.15. So if I only search for masses, and then I will so then we are expect to get a proper recovery. But here even if we search for our mass along with the eccentricity, then still you are getting a shifted recovery, and there is still not a good recovery for the hyperbolic eccentricities. But so if we
2 more minutes.
Okay, sure. So if we search for three parameters, then still the recovery is even a bit shifted. But if you do but if you do a certain reparameterization of, if you replace the b with the velocity at infinity, still you can see that the velocity of infinity can be better constant from this scenario. So we are thinking of reparameterizing our model parameters and search from the scratch. So in summary, we have developed a general relativistic, accurate, and completely efficient approach to search for the burst linear memory even in the PTA dataset. And there are preliminary injection studies are ongoing. And we have also built a completely efficient LAL compatible hyperbolic TD to search for such kind of event in the LPK dataset. And there are also further injection studies are ongoing. So thanks for your listening.
All right, thank you. Okay, we have time for some questions. Let's see. I don't see any hands raised or questions in the Q&A, so I'll use the chair's prerogative and ask the first question. Could you go to the slides where you were talking about injections of signals in PTA data? Yeah, right, okay, yes, okay. Right, so in these, so actually, could you go to the next slide? Yeah, so you said you looked at these 25 pulsars, and if I understand correctly, they were chosen because their dropout factors are all close to 1.
Yeah.
Okay, so those pulsars have a range of observed time spans, with some of them being relatively short. So I was wondering whether you've thought about doing something similar, but filtering out so that they all have long time spans, you know, because for a trajectory like this, like you were saying in your talk, not having a long enough time span to see the whole signal might be causing an issue.
Okay, so yeah, I need to still investigate on that case. Yeah, what I did not look into the time span. I chosen all the 25 pulsar. So yeah, I need to look at that.
Other questions? All right, if not, thank you. And thank you to all the speakers. We've had some very interesting talks, and I hope you all enjoy the rest of the Amaldi meeting.